Yeah, so I thought I'd talk about something, an object that I thought about most in the last months, and these are graphs, or more precisely moduli spaces of graphs. Moduli spaces of graphs. So a graph is an object that consists of two parts of information. One is a set of points that are usually called the vertices. Maybe this. And then there's the second part of information. These are edges, which one can draw as lines connecting the points. So for example, this would be a graph with, maybe I'll draw a bit more straight, with 3 vertices and 3 edges. This thing would also be a graph. And in the type of graphs that I consider, I also allow 2 edges or multiple edges connecting the same vertex. So for example, this would also be a graph for me. This is a graph. And I also allow loops. So I say that it's allowed that an edge connects to the same, back to the same vertex. And I don't care so much about single graphs, but more about families of graphs. And in particular, interesting for me is the following family. So I fix a natural number n. And then I consider only rank n graphs. Rank n graphs. And with rank, the rank is the number of basically cycles that I can find in this graph. So in this case, this graph would have rank. There's 1 closed circuit here, 2, 3, 4, 5. So for me, this would be a rank 5 graph. And now I consider the set of, for a fixed n, rank n graphs, such that every vertex has valence at least 3. This means that at every point, at every vertex here, there are at least 3 outgoing edges or half edges. So for example, this thing has rank, so this point has valence 4. This point also has valence 4 because there are 4 things, 4 lines coming out of the thing. Okay, and I want them to be connected, which means that we can find a path consisting of these edges between any 2 points in the graph. And if I take this family of graphs, then these together can be assembled into a space. And this is called, often noted, MGN, the moduli space of rank n graphs. So maybe an example, this would be an element in MG5. Let's say if n is equal to 2, what kind of graphs can we have? So we are allowed to have 2 cycles. For example, we can have a single point and 2 such loops at the single point. This is in MG2. So this is MG2. Then we can also have a graph that looks like this. So I have 2 vertices, and there are 3 edges connecting the 2 vertices. And again, there are 2 cycles, 1, 2. And then there's only one last possibility, in fact, and this looks like this. 2 vertices, then this is called a bridge, because it connects 2 different parts of the graphs together with these loops. So and in fact, if one requires that every vertex has at least 3 outcoming things, then these are the only types of graphs that one gets in MGN. But now I claim that actually this is not only a set of graphs. I mean, in the end, a graph is somehow a kind of data structure, if you want, right? You say what are the points and how do you connect them. But I now claim that you can build a space from these graphs. And so the points in this space are actually the graphs. Maybe let me go a bit more to the right here. And now I need to describe to you how I walk around in that space. So for example, this is one point in my space. So now I take a graph and assign a length to every edge in the graph. And walking around in this space means changing the lengths of the edges. For example, I could shrink down this edge here in the middle, and then I get to maybe a graph that looks like this.
So the lengths are also relevant?
The lengths are relevant, right. I start with the graphs and I equip every edge with a length, a finite length. And then graphs are considered to be close to one another if they only differ a bit by the lengths. So here I can imagine this is one point in my space and I walk towards this point slowly. There in between there will be infinitely many other graphs where the length is somewhere between this and this. And then if I continue walking in this direction, this middle edge gets shorter and shorter. Maybe at some point it looks like this. And then at some point here it vanishes, has length 0. And then you see it looks like this graph. So this way I can walk from that graph with these 3 edges to a graph with only 2 edges.
Yeah.
Yeah, and this is a continuous in the sense that every point in between those two describes another graph with other edge lengths.
Yeah.
Okay, so this gives me a space. And there are different versions of this space. And I'm interested in particular in one version that's called outer space. Usually denoted CVN. It's due to Kaller and Vogtman, were the persons who invented this space. And for this variant of the space, I do not only look at the space itself, at graphs themselves, but I also I remember the cycles in the graph. So for example, here, as I said, there were two cycles. Yeah, this is one, and this is the other one, walking around this thing. And now if I change the edge lengths of the lengths of the edges, then also the cycles, I get cycles that correspond to this in the other graphs. Yeah, so for example, here, these all would be points in this outer space, CVN. And here it turns out, if I remember these cycles, then this is an infinite space, and also in the sense that there are infinitely many, not only in the sense that there are infinitely many points between any two graphs, but actually infinitely many such forms of graphs together with cycles in them. So now I get a very complicated looking space at first, right? With a lot of graphs, and the points are, walking around means changing graphs. But it turns out that from a topological point of view, this space is very simple.
Okay.
Namely, it's what's called contractible. One often writes it like this. It's homotopy equivalent to a point. And that means that I can deform this space continuously, push it together somehow without destroying its structure until I arrive at a single point. Okay, so from a topological point of view, the space here is not really more complicated than a point.
So does this somehow mean that all graphs are similar, or?
Well, it means more that the ways of transforming one graph into the other doesn't give you unexpected obstructions.
Okay.
It's more something like this. So, well, for example, maybe one example of a thing that is not contractible. A circle is not contractible.
Yeah.
If you have another thing that is contractible first would be a line. You can push it together until it becomes a single point.
Yeah.
Now with a circle you can also try to do that. Yeah, you make it smaller and smaller and smaller, but there will always be this hole in the middle. And to get from this circle to a single point, there needs to be some kind of exceptional event, some not continuous thing, where you crush the circle together and it becomes only one point.
Okay.
And so this is not something that is contractible. Okay, but now of course you might ask, well, I have something that is a point, so I said it's a very simple space. Now in a sense, why do I do this? Why do I build this complicated space if in the end it just looks like a point? And the point is that the symmetry group of this space is very interesting.
Okay.
So the symmetry group of this space is what's called out of n. Yeah, so if I put all the symmetries of that space in a certain sense together into one object, then it gives one algebraic object that is called out Fn, the outer automorphism group of the free group. And this out is why the space is called outer space.
Okay.
So it started with this group. Right, and actually this is the direction. So people were interested in this group, and to better understand this group, they built a space that looks like this, such that the symmetries of the space is exactly the algebraic object they started with.
Okay.
That's a typical theme in geometric group theory where I work. Yeah, you're usually interested in understanding some kind of group, some kind of algebraic structure. Yeah. You try to do that by constructing a space that realizes the group as its, such that the symmetries of the space correspond exactly to the algebraic object you had before.
Okay.
And then you you try to understand that space for determining some kind of algebraic properties of this object you're actually interested in. For me, in particular, I'm interested in something related to the homology or cohomology of that group. So this is, again, an algebraic invariant. It's some kind of algebraic invariant you can associate to the group. And now my claim is that because this space has as its symmetries this group, and because it's otherwise topologically quite simple, so it doesn't have unnecessary information in it, I mean, that's a bit oversimplified, right?
Yeah.
But roughly speaking, it only has the information about this group in it. No more topological sides. And this allows you to determine these algebraic invariants of the group via this space.
Ah, okay.
So that's roughly a thing, and maybe I can say, so I'm interested in a few questions around this space and the group,
Yeah.
but maybe I can say what concretely I try to understand at the moment.
Sure.
At the moment I try to, maybe I put it down here. At the moment what I try is I try to simplify that space in a certain sense.
Okay.
So what I mean with this is that here I have a space with a lot of graphs, and I claim that I believe that certain graphs are not needed in this space.
Okay.
For example, this graph here is known not to be needed for the space. So what do I mean with, so this was in the original paper of Color and Bookman where they introduced this space. They showed that one actually doesn't need this graph. Basically the reason that one doesn't need it is that it has something like this, which is called a bridge.
Okay.
Bridge is an edge in your graph, such that there are two parts of the graph and you can only get from one part to the other via this bridge.
Ah, yeah.
And what they showed is that actually graphs with these bridges are not needed in this space.
Okay.
In the sense that if you take this space and remove all bridges, graphs with bridges, well then in principle what could happen is you have this space and there are some points in it are graphed with bridges. Now if you remove them, you might think that there are holes that are created in the space because you remove something from the interior.
Yeah.
But what they showed is that this procedure actually does not create any holes. So this thing is still topologically very simple. It's still a contractible space.
Okay.
And now what I claim, what I think is that also other graphs are not necessary. And for this I need to go to rank 3. For example, I think that this graph is also not necessary.
Okay.
And the reason is that there is this, this combination of the two edges here. This is called a two bond. So those are two edges, and if you remove them, then the graph becomes disconnected. So the only possibility to go from here to here is either via crossing this thing or this thing.
So this is some generalization of a bridge? Or?
It's a generalization of a bridge that people in graph theory look at. Yeah, they say a graph is so-and-so highly edge-connected if this doesn't exist, basically. It's a graph theoretic notion. And now, a bit simplified, I would like to say that also if you remove those graphs from that space, you don't create any unnecessary holes. So it still stays a contractible space. This is not exactly what I want to show, but it's roughly the statement. Yeah. And at the moment, I showed something similar, but not quite that statement.
Okay.
And there's another group of people who also showed something similar, but not quite that statement. But also not quite my statement.
Okay.
And
typical.
Yeah, I talked to them. I met them a bit earlier this year, but also talked to them again next week. And it's still not entirely clear to us what the connection between the two results is. So it seems like they should be very related, but the proofs are somewhat different. The result is also not quite the same. It's just that it looks very similar, and we're currently trying to figure out what exactly is the similarity and whether it's whether they're. I don't think the statements are actually equivalent, but how they can be transformed into one another.
But you would like to push it to this statement that you can remove all things with two bonds, or?
Yeah, I mean it probably won't be. I want to push it to a similar statement that is a bit more technical to state.
Okay.
Exactly, but it is about removing these graphs. I mean, I don't think it will be true that one can just remove these graphs.
Okay.
But I want a statement that makes it true, basically.
Okay, and is it always like if you are in dimension 3, then you can remove two bonds, and do you expect that you can generalize this to higher dimensions? Or?
Yeah, with higher bonds, you mean?
Yeah.
Yeah, of course. Yeah, that would be. So it won't be quite true. It won't be entirely true that the space is the same. But my hope is that for a related question where you don't study this space but just its boundary, one might be able to show a similar result.
Okay.
But a lot of more technicalities start to arise there. And okay, that's a bit hard to explain now, but basically the problem is this degree at least 3 condition.
Okay.
Okay, now this is a bit hard to say in a simple way, but if you think about these 3 bonds, so those are two bonds would be 2 edges. If I remove them, the graph gets disconnected. Now take a graph that looks like this and has valence. So something is going on here, something is going on here. Maybe make it more concrete. Well, now I need to build some graph around it. But this is a vertex and there are exactly 3 edges coming out. Now, if I remove these 3 edges, then it will just always be true that the remaining graph is disconnected, yeah? Because the only way to get to this point here is via these 3 edges. And this is not something that can happen with a 2 bond. Because in the definition of my graph, I excluded the possibility of these kind of things. So, and this is a source of difficulties that makes it, well, certainly the statement is not true on the nose if I say it with 3 bonds. Variants of it might be true, but it's a bit hard to realize technically. And that's the relation between this, how to disconnect the graphs here.
Cool. Yeah, thank you very much.